Good morning, everybody. It's my pleasure to start the day with our keynote speaker, Dr. Leong Chu. He's the director of the Advanced Imaging Center at HHMI Janeila Research Campus, and he's also the founder of the Africa Microscopy Initiative and founding member of Bioimaging North America and the Imaging Southeast Asia. And he's really actively engaged in driving microscopy all around the globe, and he's going to tell us a lot more about that in his keynote address. So welcome.
Well, good morning, everyone. Can everybody hear me okay? All right. So this is when Claire asked me to give this talk, and he said, can you sort of bridge the BINA and GBI? And I realized that the two conferences has two very different themes. So it is going to be an interesting talk. We'll see how it goes. We spent quite a few hours and sessions and talking quite a bit about the impact of imaging infrastructure, imaging network, and imaging scientists in general. And over the past 3 days, what we have been listening is strategies on how to convince your stakeholder the importance and the impact of everything that we're trying to do. So I'm going to share a paper with you. I'm not going to dive too much into it because it has been published. We take a different approach. We do a mental exercise by removing everybody in this room. Just make all of us disappear from the surface of the earth. We remove all your imaging center, we remove your community, we remove your infrastructure, we remove your imaging center. Now imagine the impact on biomedical research in general. And that is another way. Sometimes if people are not listening to what we are trying to sell, just remove it. So we wrote this paper. I want to talk a little bit more about just the added value of imaging resources. And it is written in such a way that hopefully you guys can actually weaponize it when you talk to your university leadership. Pretty much every excuse that I've heard in my entire career, I pretty much preemptively addressed it. So hopefully you can take advantage of it. Like I said, I'm not going to dive too much into this particular paper, and I want to focus on how this particular talk can potentially, hopefully, bridge these two conferences. So if you look at the GBI conference theme for this year is to focus on sustaining imaging infrastructure, network, and facilities. And many BINA delegates are starting to stream into this room. And the BINA theme is to explore cutting-edge advancement and strategic visions for the sustaining and sustainable development. So if you look at this two themes, the only word that pretty much binds them together is actually sustainability. If I can advance my slide. So to many of us, sustainability means how we can find more funding, right? But I want to sort of get everybody to think a little sustainability from a completely different angle. No matter what we're doing, and whether in imaging or in business or in anything, really the only thing that sustains sustainability is demand. We have to create demand. If scientists continue to want to use imaging as a tool, funding will follow. And as a bioimaging community, we have to figure out as many ways and as many effective ways as possible to keep this demand coming. And so in order to create demand, scientists actually have to adopt the tools that we're trying to sell. It is either could be a new tool in your imaging center, or you are an instrument developer, you are developing new tools. And if you're funders, you have funded a very successful technology. You want the rest of the world to use the technology that as a funding agency you have successfully funded. The word adoption has to be in your mind. And in order to adopt that, we have to do dissemination. And dissemination is something that this community does exceptionally well. And please don't stop doing that, because so dissemination is quite important. And so my talk will be divided into 3 sections, roughly. Basically, the first one that we're going to talk about is dissemination and capacity building. And as I mentioned before, this community is exceptionally good at building capacity, at building infrastructure, and bring this community together. Now, you have seen The GBI world map quite a bit. I added quite a few more because not all of them are GBI. Frankly, this is about as much as I can jam into this map. The more I jam into it, it will not make any more sense. So if your network is left out, it is probably because PowerPoint doesn't allow me to aesthetically jam more label in there. So there are significantly more, right? So now the question is, if we are that good with dissemination, in fact, we're so good at dissemination that we have successfully convinced many, many funding agencies to make sure that sharing plan, technology sharing plan is in every grant that they are trying to fund, right? So why is technology not being adopted at the speed that we hope that it can? And there are a couple of misconceptions. So the next slide, I'm actually going to be talking to the funders in this room. So there are some common misconceptions. Many people, including your university leadership and to some extent some funders, think that as long as you have an advanced technology, this will draw people to use it. That is not true. Advanced technology alone usually does not provide sufficient draw for biologists to come and use it en masse. So we have to continue to convince people that technology is extremely important. And the other thing, which I think is also important, is the fact that technology sharing is not really technology dissemination. They are two very, very different things, right? No instrument developers in their right mind would develop something and say, nah, I'm not going to share it. Everybody is going to share it. But the thing is, sharing is just not enough. It takes people in this room and the community that you represent to really, really disseminate technology successfully. So many of us congregated at Janeila last year in May to basically explore this particular topic of what is standing in the way for all of us as a community to continue to disseminate microscopy technology, especially to resource-constrained communities. So as you can see that the authors, most of them are actually in this room. So this is obviously a worldwide view. So what I'm going to talk about next is how, as a community, we can no longer just set our sight purely as at the point of we have successfully doing dissemination. The next step, the next goal that we have to set our eyesight on is adoption. We have to get biologists to adopt the technology so that we can create demand in the future, and that leads us to technology adoption and scientific outcome. If you speak to a lot of the funders nowadays, what they want to see is scientific outcome. If we give you a lot of money to disseminate, will it translate into scientific outcome? And one of the things that we are continuously trying to fight, as was mentioned by the first keynote, is this bibliometric type of metric is actually not very good. It's how many papers have you published? Because there are a lot of technologies out there that are not really, and just immediately results in papers. Some of the microscopes are developed with very focused application in mind to detect disease, to diagnose disease in the field, and they save life. And those has to be translated into measurable scientific outcome. And so this is something that we as a community have to grapple with and to be able to convince the funders that it is more than just papers that can measure outcome, right? So to come back to my point is what are some of the barriers that's standing in the way for microscopy adoption, especially in resource-limited regions of the world? There are quite a lot of them. One of them is the lack of awareness and the lack of expertise, resource and funding, which hit all of us. Reagents. Many people don't, for all of us in the global north, sometimes we don't think about how difficult it is to get reagents into the hands of scientists in places like in Africa, where here, if we place an order, we'll get it in 24 hours or 48. By the time you get it in 48 hours, you get pretty pissed off. In many places in the world, people wait for 6 months to 9 months just to get a reagent. And by the time they get that reagent or antibody or whatever in their hand, that reagent is completely useless. It's expired. It's no longer functioning. So that is something that is very difficult to deal with. And then there's a lack of equitable opportunities and accessibility, which is something that, initiative like the Africa Microscopy Initiative, Imaging Southeast Asia, and a lot of others are trying to address. And the lack of support in general. Data handling is obviously, there are a lot of data scientists here. And we continue to hope that organizations like NewBias and GloBias can continue to play a big role in helping and provide global support to scientists in need all over the world. And the lack of continued accessibility, the fact that you give somebody access to a very high-end, powerful microscopes, sometimes they actually don't want to use it because they realize that if they start something at your imaging center with a very high-end, very powerful instrument, when they go back, they can no longer continue that work, right? This happens all the way at the AIC level at Janeila. This is a question that Allison loved to ask me many, many times. What am I going to do when I go back? So together, all those attendees at the Janeila conference have come up with this sort of a roadmap that we have to translate dissemination into adoption and into scientific output in general. So we're very good with dissemination. I'm not going to talk a little bit more about it anymore. I want to spend a little bit of time talking about adoption. So there are some necessary ingredients. We have to do a better job integrating scientific and imaging communities. And if you look across this room, we're preaching to the choir here. We all know the power of microscopy, but we rarely go out and interact with the biologists at large. And we need to insert ourselves in the conferences like ASCB, in developmental biology, something that Bina actually does pretty well, but we should continue to do that, and we cannot just talk among ourselves. We actually have to talk to people who will need our technology. And I also want to spend a little bit of time talking about targeted and contextualized training. Many of us run workshop, but a lot of times our workshop are not contextualized. We teach what we think is important, but we don't think about whether or not the recipient actually will benefit from what we're teaching. And then a few others, which I'm going to hopefully be able to cover. So I want to focus on targeted and contextualized training. If you're going to contextualize your training, you actually need to know who you're talking to. So we are quite lucky in the sense that we have run quite a few successful workshops, and through the application form and the process, we have gathered quite a lot of information from scientists worldwide. And so this data come from the first Imaging Africa workshop, where we have close to 700 people applied. And then we also have a Janeila bootcamp. And then the second Imaging Africa workshop, followed by Imaging Latin America, which we run in Uruguay. And then another Janeila bootcamp. And then the 2024, we run an Okinawa workshop, which actually precipitated into the formation of the Imaging Southeast Asia. And then lastly, the molecule to human workshop that was funded by CZI and that was conducted in Copenhagen. So when we pull all this information together and remove all the undergraduate applicants, we have close to about 2,500 people represented worldwide. Now, caveat, there are countries where a lot of good science are ongoing, but they're underrepresented. China is one of them. Russia is not represented at all. Turkey is not represented, and you can pick your own country that are not represented. There are also countries that are seriously overrepresented. Nigeria is one of them. So take that with a grain of salt. But to come back to my point is, how do you contextualize your training to your target audience? If you look at the Northern Hemisphere, if you look at the North America continent, for example, for those who can't see it at the back, this yellowish orange sign is cell and molecular biology. Again, with a lot of advanced imaging tools in North America, many scientists are going into more mechanistic insight of using microscope to tease out the underlying biological principles. So cell and molecular biology clearly is a very big deal here. Neuroscience, and then there are also quite a few core facility people, again, reflecting the strong core facility structure on this continent. Now, as you would expect, Europe is pretty similar, right? And mirrors the situation in North America. And then when you go to Asia, it is starting to change a little bit, but not by much. Cell and molecular biology still stays pretty big, but there are a lot of other things that pops up. Plant biology is starting to become important, especially in countries like Vietnam and Philippines, where agriculture reigns supreme, right? And then when you go to the Southern Hemisphere, Oceania, then you start to see the diversity drop a little bit. But again, core facility over there in Australia, especially, core facility structure is very strong. We have heard about that. Cell and molecular biology is still there. And then when you go to Asia, the Latin America, the diversity comes back. However, when you go to Africa, now it changes. So there are quite a few of you who have been recruited to actually serve as a mentor for the Partners in Teaching Program for Africa Microscopy Initiative. You know who you are. So all the mentors that you're going to start doing this next year, you have to start thinking about what is important for your trainee, for example. And you have to really, really focus on what is important to them. And then likewise, when you look at the proficiency of the various type of microscopes that they think they know, blue is good, red is mean that they are not proficient. Pretty much everybody knows what a bright field microscope is, so it is pretty even. As soon as you get the fluorescent wide field microscope, Asia drop a little bit, Africa drops quite a bit. Confocal, same thing. When you get to advanced technology, then Latin America, Asia, and Africa drops. Analysis is something we have to take very carefully because analysis means different things to different people. For us, it could be AI driven. For them, it could be just with a cell counter, but clicking by hand. To them, that is image analysis. So you take it with a grain of salt again. But again, when you're teaching, especially if you are out of your good intention, decide to do global outreach, or if you're running an international workshop, you want to make sure that your message got across. And this is very important because a training course that is not tailored to the target audience does not serve its purpose. It actually serves more to alienate the attendees than to inspire them. So it is you do not want to turn people off, because if we're going to push our effort all the way to adoption to create demand, you have to get them hooked, right? I've also seen many workshops that stress a lot on technology rather than on science. You're training scientists, spotlight their science. What we're trying to share with them is the tool to enable their science. We're not spotlighting the technology. So this is quite important. You emphasize how informative results and quantitative results can be achieved through rational microscopy experimental design. That is more important than what a min-flux can do and how STAT works, for example. And for audience in underserved community, the tools that are being introduced must be very topic specific, and it has to be locally relevant. Don't talk about STAT in sub-Saharan Africa, important, but it's not immediately relevant. And understand the local challenges, right? The scarcity of reagents, the computing power, the internet connectivity, even stability of electrical power, and all the extremely limited funding. Now, it's not like this community doesn't fight to solve this problem. In fact, this is the list of low-cost microscope that overall the worldwide community has developed. There are significantly more. I just put this in because it makes this two table look symmetrical, that's it. There are significantly more. So if there are so many cheap microscope out there, why is microscope not in the hand of every scientist who need it? So we published another paper that talked about a roadmap for widespread adoption of frugal microscope. And the word frugal microscope become important. So instead of talking just to the funders now, I want to share some of these things with some of the developers of instruments in this audience, and as well as those listening out there, especially if you're developing low-cost microscope. The fact that something is cheap does not make it affordable. A cheap microscope that is wrongly disseminated to a low income country actually can be very devastating. Because one thing that many of us don't think about is in very low income country, they only have $1,000 or $2,000, if that, to spend on their microscopy infrastructure. If you are trying to sell to them or brand your invention because it is cheap, but it doesn't serve the purpose, they have just wasted that $1,000 or $2,000, and that opportunity will never come to them again. So they can ill afford a cheap microscope. So one thing I want to sort of, in this paper that we talk quite a bit is, when you are trying to give microscope to scientists, and the whole idea is to empower scientists in lower income country, you really want to develop a research grade microscope. And a research grade microscope is a microscope capable of generating reproducible, quantifiable data across a wide range of specimens. And that is what a research microscope is. There are a lot of really, really powerful diagnostic microscope than Fletcher's LOA scope, for example, that trying to detect this parasite in river blindness that has saved millions of lives. High impact microscope, but it's not a research grade microscope. Foldscope, for example, is an extremely powerful educational microscope, but they are not research grade microscope. To make a microscope frugal, not cheap, but frugal, is a system that can basically achieve the same performance as an equivalent commercial system, but with substantially lower cost. That is what a frugal microscope is. It doesn't have to be just a few dollars. It may be a little bit more expensive, but you do not compromise the performance of that research grade microscope. And I hope we can take all of this into consideration as we continue to develop important tools to empower our peers and our friend in lower income countries, and for also funding agencies to really filter the low cost microscope a little bit more. And as I promised, I want to sort of bridge it to the BINA audience, which is to look ahead, what is in store in the future, since the theme of both of conferences is Imaging 2035. So I want to give you a glimpse of what is coming. This is by no means comprehensive. There's no way I can talk about all the upcoming technology in 5 minutes. So I'm going to sort of categorize them. And one of them is the multimodal and correlative imaging, right? And so here we are combining, thank you, Claire, super resolution at cryotemperature, so that we can actually look at the junctional complex. And then we select the region for focus ion beam SEM, and then we start milling it. So now you're looking at CLAM that combines super resolution and volumetric EM. And as we are scanning in, we start to make quite a bit of discovery that ER is making physical contact with adhesion molecule, so on and so forth. And then that leads us into the discovery of this tripartite regulatory structure that basically integrate organelles, intermediate filament, and adhesion molecule all into one tripartite regulatory domain that lead us to this paper. And so this is something that will continue to be developed. So we can no longer just think about one microscope standing alone, because many microscopes have to now work together to pursue the deeper mystery of life. And then many of you are doing clearing in your facilities. Clearing is no longer sufficient. Many of you have heard of expansion microscopy. If you have not, basically it is sort of a clearing technique, but you expand the sample as well. You infuse into the sample with literally a diaper material. and you cross-link that, and then when you add the buffer, the diaper material expand, and you basically expand your sample. And the idea is that you can now massively increase the resolution of your microscope without changing the microscope, because you just expand the sample. The problem is when your sample get that big, you have to start increasing the throughput. Otherwise, it's going to take forever to scan your sample. So the best way to increase your throughput is to use a light sheet to scan it, because light sheet is fast. The problem with light sheet is that it cannot penetrate very, very deep. So you have a very big sample, you can only scan the top layer. There are a lot of information at the bottom. And so Ray at University of Illinois, Chicago, in collaboration with Eric Betsick and Gokul, have basically developed this technique that basically, if you create a new kind of gel chemistry, the gel can become photocleavable. So you bring in a lightsaber, like Star Wars. And after you scan the first layer, the lightsaber will come in and it will liquefy the top layer of the expanded gel. And then the stage move up, and then you scan again, and then the lightsaber come in, you liquefy the top layer again. So you see it liquefy, and then now you can scan the whole sample. But no matter how you achieve this expansion microscopy, large data are coming. Fast and furious, they're coming. So as core facility, we have to start thinking about what to do. And then the other thing is integration of microscopy with other omics, right? And many of you have heard of spatial transcriptomics. So most of the time when you do transcriptomics, you can only do one layer. James Liu at Janeila has developed spatial transcriptomics in 3D. And so again, all this data are coming, which leads us to AI. At some point, we all have to deal with AI. We cannot stop AI. So now the good thing is that AI is now completely permeated the entire workflow of microscopy, from experimental design so that you can use AI to generate ideas for experiment and systems, and then use AI to build the microscope, create automatic pipeline, run the experiment so that you can generate AI-ready data, create experimental model, create new knowledge, and then use AI to drive this cycle over and over and over again, right? And with that, I'm going to give you an example of how AI plays a role in microscopy directly, which is the development of smart microscopy. Many of us deal with biological events that are usually pretty rare, and you have no idea where that event is going to happen and where it is going to happen, for example, tumor invasion or cell division, for example. So you can train AI to be able to predict when it's going to happen, right? So this is a work by Wesley Gunn where you can only look at cell division. This is where I think I want to sort of give everybody who is running a core facility a sort of a glimpse of what is going to happen in the next few years. If you look back in the past 10, 15 years, when your university leadership come and tell you, hey, we have to start keeping up with the technology, you can secure funding and get yourself a stat, get yourself a MinFlux, get yourself a lattice light sheet. You're pretty much on top of the technology, and as long as you provide service. In the next few years, to stay on top of technology means that you have to spend 6 months to a year training AI to be able to do those experiments. The questions for all of us, and I don't have an answer for that, is this the job of a core facility? If it is not, then we will be left out. If it is, are we ready? And I don't have an answer for that, and I want everybody to think about that. So if you look across the literature, there is no textbook that talk about AI in microscopy. So we're writing one. I'm not going to tell you where to find this textbook because we're not ready. There are only 3 chapters been uploaded, so it's kind of embarrassing at the moment. Hopefully, we will be able to get the entire book ready by the early next year. Quite a few authors are actually in this room. So this is the first AI in microscopy textbook, and it will be completely free. It will be online, so watch out for the announcement. I'm not sure if I'll have time to finish the rest of the talk because of the glitch. Keep going? Okay. She told me to keep going. Okay, so I'm going to rush through this. The other thing we have to think about also, again, a message to the funders, is there are more and more transformative technology being developed. 10 years ago, if you tell people that, well, we're going to clone a microscope and it is pre-commercial, most biologists will freak out. Nowadays, many departments, many core facilities now start to adopt pre-commercial instrument, so that is one of them. And to really, really pave the way for transformative technology to be widely accepted takes more than just validation. Validation is very important, but there's actually a lot of risk. As Vlad have mentioned in his video, is many transformative technology are developed in very restricted disciplinary silo. They are usually developed in physics lab, and they never get to see the light of day because physicists a lot of time don't have connection to biologists. And then they are always under-validated. And sometimes they have mismatch application because there's not a team there that can serve as a filter so that the transformative technology actually get the right kind of application to test it. And everybody heard that this is an awesome technology. Everybody want to test it. And believe it or not, that hype kills a transformative technology faster than a regular conventional technology. In fact, there's a conundrum, is the more transformative, the more disruptive a technology is, the more susceptible it is to hype. Because everybody think, wow, this is gonna solve every problem under the sun. They tried it and they get disappointed. And nothing kills a technology faster when a few big names in the conference walk around, I've tried it, it doesn't work. And that is very unfair to any disruptive technology. And precisely because they are not yet being proven, there is always a hesitancy in funding. So for most of us, there are three ways to get our hands on transformative technology. Either you buy it if it's available, sometimes you clone it, or you try it at places like the Advanced Imaging Center at Janeila. And so the last slide, again, is for the funders, is if you really want to pave the way for truly transformative technology, it cannot just be a one-off investment. This is a concept that has not yet been mentioned anywhere. If you really want to pave the way for a very transformative technology to get into the field, you need this comprehensive programmatic stewardship. The keyword here is the stewardship. You need a multidisciplinary ecosystem, a very expert support team that know exactly what that microscope can or cannot deliver. And you have to do very serious outreach and very rapid feedback loop to the developers, and then institutional programmatic support. And that cannot just be a university say, well, do it when we get funded. The university have to make that commitment. And that has to be a no-cost open access. So that is all I have. I'm gonna leave this movie out for you to take a look. This is the kind of data that will likely be in 2035 and as a commonplace. Thank you very much.